there's still going to be many layers of a stack, but I just think ZK is going to be like the base glue for everything. And like, basically, yes, like having truth communicated everywhere. And hopefully that leads to like better security, like no more hacks, and like leads to like, oh, there's not rollups that are just multi-sigs with like no fraud proofs and stuff. It's just like everything. Hopefully we'll just use ZK and
Which
it'll be
rollup are you talking
awesome.
about?
Hey.
We don't name names. We don't name names.
Hey everyone, this episode is brought to you by Sei, the blazing fast parallelized blockchain which is unlocking Solana-like performance for the vast ocean of ETH devs out there. Now, you're going to be hearing all about Sei and their new V2 upgrade, but if you take away one thing, the EVM is here to stay. There are some problems with it, which we're going to get into later in the episode, but Sei, and especially their V2 upgrade, is helping solve that. So thank you very much, Sei, for making this episode possible. Hey everyone, this episode is brought to you by Uniswap, delivering the best on-chain trading experience in crypto, period, bar none. One thing I want to call out is the Uniswap extension. So say goodbye to these days of these annoying sort of pop-up wallet extensions. You lose your place trading, you have to open it back up. Uniswap now has a nice, sleek sidebar that persists no matter where you are on the web. It's much easier to use. If you click the link at the bottom of this episode, you can join the waiting list. And I'll see what I can do to get you moved up that waiting list. But definitely go click the link, check it out.
All right, everyone. Welcome back to another episode of Bell Curve. Before we jump in, quick disclaimer. The views expressed by my co-host today are their personal views, and they do not represent the views of any organization with which the co-hosts are associated with. Nothing in the episode is construed or relied upon as financial, technical, tax, legal, or other advice. You know the deal. Now, let's jump into the episode.
Hey everyone, welcome back to another episode of Bell Curve. Today, Hart and I are going to be interviewing Uma Roy of Succinct, and we're going to be doing the long-awaited, much talked about already on this season, Zero Knowledge Proofs episode. Now, this is a really interesting episode because, as many of our guests have already brought up this season, ZK has massive implications for cross-chain interop. And so we get into all the details about how that's going to work with Uma and unpack the implications. And for those of you who pretend like you know what ZK actually is, but you don't, aka 95% of you, we spend a good amount of time in the beginning of the episode just reviewing what ZK is and talking about the ecosystem, which is super, super interesting. So really excited to get into this one with Uma and Hart. Thanks for listening, guys. All right, everyone. Welcome back to another episode of Bell Curve. Today, Hart and I are joined by Uma from Succinct. Uma, welcome to the show.
Hello. Thanks for having me.
Yeah, we're really excited for this one. Hart and I have said, I think at the end of every single episode so far this season, all right, we need to do a ZK episode, and there is no one better to do that with than you. So I'm going to start with, Uma, I'm going to give you the caveat here that we don't treat me basically as you would a 5-year-old who knows very little about zero knowledge. That'll probably be about the right level. Actually, as a funny story, flying back from ETH Denver, Hart's left. I told Hart this. So I was flying back from ETH Denver, and I was like, I'm going to do some research for this episode with Uma. And I started off by reading, ZK Sync actually put out a 5-year-old picture book description of what ZK Tech is. And some guy was saw me reading that and was like, hey, are you trying to learn about ZK Tech? And he had led the investment into Risk Zero. And I talked with him about ZK for the rest of the podcast, or that flight, but still pretty embarrassing to out myself.
A very smart ZK guy, Uma. I won't dox him, but it was just very funny. He's sitting beside Mike watching his picture book and being like, hey, let me actually tell you about ZK stuff.
Yeah.
That was his flight.
Yeah. That's so funny.
Yeah. So with that, Uma, can you just give us at a high level, just explain to us, what are ZK proofs, if you had to describe them?
Yeah, so I guess at the highest level, a zero knowledge proof does two things. The first one that I'll start with is I have some computation or some function, and I want to prove to you that when I run that function on a certain input, it results in a certain output. So as an example, it could be when I do this hash 500,000 times on this input, it results in this output. It could also be a state transition function where when I take a state root and a bunch of transactions, when I run those transactions, it results in a new state root. So I want to prove to you some computation, and you want to verify it without having to redo the computation because the computation can be expensive. A zero knowledge proof lets you basically prove to someone else this function, when run on this input, results in this output. And then the key part is it's succinct, which means that when you verify the proof, it takes much less time than it would to actually do the original computation.
Got it.
So On that, Uma, is it like accurate? One thing that somebody told me that I think makes sense, but I want you to verify this, is to think of it like a compression technique in a sense, where I'm compressing this giant computation into something I can run in linear time. And that's the succinctest property. So first of all, do you agree with that?
Yeah, I mean, except it's like constant time. But yes, so even better.
Okay, yes. So I have a constant time proof of this incredible, like it could be an incredibly complex computation. Doesn't really matter how big the computation is. And I can compress it into something that is easy to verify.
Yes.
And that's the succinct property, which is the name of your company, Succinct Labs. But also, why don't you talk about like the zero knowledge bit too? Because like, I think for us, when we're talking about ZK for interop, I don't think we care about the zero knowledge part. I think we care about the succinct property. But like, we might as well mention it because we're on the pod, right?
Yeah, that's exactly right. So the other thing I was going to mention is you have the succinctness property. And then the other thing you can do is you can prove that I have some function when applied to some inputs results in an output, but the inputs can be hidden to the final person. So as an example of that, you can say like, I know the password or like the key to something. I'm not going to tell you what the key is. So I'm going to hide that as part of the inputs, but then it results in like some output that the verifier can understand. And so that is like the zero knowledge property is the verifier doesn't need to know what all the inputs are.
And Uma, could you just briefly explain the concept of circuits in there as well and what some of the computation is? Honestly, not even super relevant for this, for the what we're going to talk about here, but like I'm just for the audience, I'm curious how it works.
Yeah, so people talk about this concept of circuits in zero knowledge proofs. Basically, if I want to like historically, if I wanted to write a computation in a way that I can generate a zero knowledge proof of it, I'd have to write the computation as a circuit. A circuit is just like a fixed computational graph of your logic. And it's like a concept that exists even outside of ZK. Like there's like, in EE, there's like circuits and things like that. But basically, to generate a zero knowledge proof, you need to like format your computation in this like very structured way, and that's kind of why you have like all these DSLs and SDKs and like all this like specialized stuff for generating zero knowledge proofs. And so a circuit is just like a fixed computational graph of your computation that is an easy form to generate a zero knowledge proof of, if that makes sense.
Yeah, I think this is where the circuit stuff is when we start getting into the moon math. But I think at a high level, right, for this pod, Mike, there's this way that historically, Uma, tell me if this is correct. There's this way historically you need to describe the logic of your function in order to be able to generate the ZK proof.
Yes.
And actually, maybe that can then lead into kind of the frontier or state of the art of a lot of the ZK stuff is abstracting away that circuit generation or making it so that the average developer doesn't need to build circuits anymore. Right? I think you chanted death to circuits. I think you did that on a panel with me.
I
Right?
did. Yeah, so historically, basically, if I have some function, say I could describe the function to you. I could be like, Mike, I want to prove that when I take some number and I hash it 50,000 times, it results in this answer. For me to actually generate a zero knowledge proof of that function, I can't just like write it in normal code. Like I can't just use a normal out of the box hashing library. What I'd have to do is I'd have to write it as this like circuit in like some sort of zero knowledge proof library in order to be able to generate the zero knowledge proof. And that'd be really annoying. Like if you look at circuit libraries today, it's really annoying. You have to like basically rewrite your computation in this like fixed graph. It's very bad basically as a developer experience, and it takes a lot of time and it's very intensive. And then with the frontier of today, and especially one of the things we're building at Succinct is this open source ZK VM called SP1. But what that lets you do is instead of having to like write all this hand rolled circuit stuff, you can just write your normal computation as you would with like normal Rust code. And then you can generate a proof just based off the normal Rust code. So that's kind of like the frontier of where zero knowledge proofs is heading is like instead of having people do this really specialized moon math stuff, you just write normal code and any programmer can use it.
So where I want to start to transition here, Uman, I think and a sort of a powerful effect of zero knowledge proving as opposed to the way that computing has worked historically in crypto is where the computation is taking place. So historically, the way a transaction gets submitted to kind of this public blockchain gets gossiped around in this mempool. A bunch of nodes within the Ethereum network sort of take those up, execute them, package them into a block, but everything happens within this one virtual machine. And one of the side effects of what we're describing here, and what you just mentioned with what SP1 allows you to do, is it allows you to have many different virtual like machines or sort of computing environments. A lot of computation gets done off chain, and then the proof is submitted on chain. And one of something that allows you to do is to knit together these very different execution environments, which has historically not been super easy to do. And that's where I think we want to drill into sort of the interoperability piece. But before we even get there, I would actually just be curious to understand, there's a lot of new infrastructure when it comes to this zero knowledge space. There are proving networks. There's like new types of applications that leverage ZKPs. So can you just kind of give us a sense of like, what does the landscape sort of look like? What are the different buckets that exist in this new ZK world?
Yeah, so there's kind of like the app layer that uses zero knowledge proofs. And I actually think there's many different types of applications and infrastructure that can use ZKPs. So I think, for example, for bridging, like all bridges can use zero knowledge proofs, and maybe we'll like dive more into that later, considering this is like focused on interop. I think all rollups, I think people are probably really familiar with ZK rollups. I think all rollups can use zero knowledge proofs as like a validity mechanism. Then there's like other zero knowledge apps that are more focused on like the privacy aspects. So I think Tornado Cash is a good example. But then there's like other ones, for example, like identity applications where you kind of prove like, hey, I belong to this set of people, but I'm not going to tell you exactly who I am. And that's just like a blockchain application. So not in the infrastructure category. So there's like all these consumers of zero knowledge proofs who use them for like validity, security, or like privacy or whatever. Then there's like the actual proof systems that basically people use to like express their function that they like care about proving. So there's like various different proof systems, and then there's also like ZK VMs where instead of having to like write all your stuff custom in a proof system, you can just like write normal code and then have it proven in a particular ZK VM. Then there's like the proving networks or infrastructure to actually like generate the proofs. So it's kind of like you're an application, you write your zero knowledge you write your computation that you want proven in a zero knowledge proof in a proof system or in a ZK VM. And then you actually have people generating the proofs. And so that's kind of where proving networks come into play, is they like connect the people who are consuming the proofs with the people generating the proofs. And the people who are generating the proofs right now, it can look like companies like us, like we just like run some cloud provers on AWS, but it can also in the future look like hardware teams who are creating specialized hardware for zero knowledge proofs that like can really accelerate the proof generation time. And then they can like basically be the suppliers of proofs. And then the marketplace layer or network layer is like basically I see like the shelling point where these proof consumers and applications request proofs, and then you have like the proof fulfillers who are generating the proofs, who are like the hardware teams or people like us with our cloud infrastructure actually generating the proofs and fulfilling them. So that's like kind of like top to bottom the layers of stack, if that makes sense.
So to summarize this, so your applications, two use cases, privacy use cases, and I'm going to call it like compression or succinctness use
Like
cases.
scaling use cases.
Scaling use cases. So, and again, going back to even how you're explaining ZK, for me personally, trying to understand how the zero knowledge works for the privacy part, that's what makes my head hurt. Like I still haven't, it's still hard for me to understand how you can prove something without telling anybody about it, right? But I kind of, but anyways, there's the privacy use cases, which for our pod and for the multi-chain kind of end game, we're not going to talk too much about. And then there's the scaling or proving a complex computation succinct property that we are going to talk about. Okay, so those are the applications. And then your proving system, is it right when you talk about a VM, is it right to, like, if I make an analogy for our audience, it's like, are you using like Linux or Windows or like the operating system you're picking, right? And here you're specifically talking about the math or the math framework that's being used for this ZK proof. Yeah.
Yes, exactly.
Okay. And then once you pick that, you've got to actually do the work to generate the proof, and that you're calling that proof generation. And then there's this idea of prover networks where effectively we're going to have different provers in essence competing, kind of like a marketplace.
Yep.
to see who will generate that proof. And then you have your proof, and then you can go and use it. Yep.
Yeah, that sounds about right.
Cool.
So I have a question about the prover networks in general, and what I ultimately want to understand is like the cost of proving today, and like where I understand that that's trending down, but like as specific as we could sort of get about that. I mean, who are the types of entities that are running these proving networks? So obviously, Succinct is running one. Are there going to be eventually like almost Chorus One or Figment like entities that sort of spin these things up? Is it actually going to be like chains themselves? Like who ultimately runs these sorts of things?
Well, I think it's not like we are running the proving network. I think it's like we are designing a proving network and protocol, and then there will be entities that participate in it. So, for example, it's kind of like you wouldn't say like Celestia runs Celestia network, like Celestia
Mm,
network's a thing, and then there's node operators that participate in that network, and then there's like users that participate in the network and like post blobs. So it's very similar. There will be like Succinct network that's like a decentralized protocol, and then on one side you have like node operators who are like running provers. And yeah, I think like Figment or Course One or traditional node operators, like maybe they could get into ZK proving and like start running provers on the network, and they will get paid for generating proofs. And then on the other side, you have like applications and users submitting proof requests to that network and being like, hey, I want this proof. So those are kind of like the two participants in the marketplace. It's like the applications who want proofs and then the people who are actually like generating the proofs.
got it.
And they could include like traditional node operators for sure.
Hey everyone, wanted to give a big shout out to today's title sponsor, Sei. Now, I want to talk to you guys a little bit about why I think Sei is cool from a design standpoint, a big problem that it solves for ETH devs out there, and then some cool stuff that Sei has coming up. The reason I like Sei from an architecture perspective is, again, it's a very fast blockchain, parallelization, all of that stuff, but Sei has essentially been custom building block space, which is for consumer apps and dexes. Now, they have some very cool features which enable that. So twin turbo consensus, optimistic parallelization, Sei DB, all of this stuff allows you to reduce the time to finality, make for very, very fast transactions. So if you're building a consumer app or a DEX, this is basically the blockchain for you. If you've been building in the EVM, you love the EVM, but there are some restrictions about it that don't support your app. So maybe you can't do fast enough transactions or it's not parallelized, whatever it is, you can now take all of that stuff that you built. You don't have to start from scratch and you can build it on Sei. Now, recently they've launched V2, but also public DevNet. So the way that you can follow that and keep up to date is go and follow Sei Network on Twitter. All right. Thanks, guys. What are the economics around proving? What does that look like today?
Yeah, so I think for some ballpark numbers, I think right now, for example, we can just take a few different applications. So one popular one is bridging. At Succinct, we've written a ZK Tendermint like client where basically we verify like that in a Tendermint consensus protocol, enough validators have signed off, and that lets us do like trust minimized bridging between networks who use Tendermint, like Celestia or DYDX or all these other people, to Ethereum or something like that. And so the proof generation costs for one of those proofs is actually really cheap. I think it's like a couple cents, if that. And so it's very, very inexpensive today, just in terms of raw compute costs to generate a proof.
So wait, Uma, that's cheap enough that I want to like push and understand that. So this is like, to be clear, this is generating a ZK proof of a Tendermint consensus. And you're saying that the computation costs of that are like a couple cents, which is awesome. For context, to kind of share with the audience how quickly this is developing, like a year ago, what do you think the computation costs would have been on this?
Or yeah, like a year ago, to be honest, is like kind of impossible. Like it just the circuits and like all that kind of stuff didn't exist.
Okay.
And then yeah, we were like one of the first teams to like kind of put all of that together and like get it working end to end. Like I think maybe a year or a year and a half ago, people thought it's like impossible. Like they would thought like, oh, the proof generation would take like hours or something like that. I think our proof generation time takes like 5 minutes. It is on a pretty big machine, but like with cloud costs, the machine probably costs like, a couple bucks an hour. And so the costs are very cheap. It's like, a
Okay.
couple cents.
So, and actually, we should go into this too, as Mike's pushing on the economics, which I really want to hear you describe more as well. It's proving time is directly related to computation costs, basically like how long you got to run this beefy machine for and how much that costs. So your 2 cent proving time here is like 5 minutes on a beefy machine. in AWS right now.
Yeah. Yeah, that's how we compute cost. It's like it takes 5 minutes to generate your proof. The machine's like pricing is like $2 an hour. You just do like that math. Other examples people might care about is for a blockchain, for example, approving a state transition function of, for example, a ZK EVM. Recently with SP1, we released some numbers that showed that the proving cost per transaction, and again, this is like the same methodology where like you take the proving time on a beefy CPU and you just say like the CPU is a couple bucks an hour, and so you do that math, amortizes to like around 1 to 2 cents per transaction. So like the proving cost to prove the validity of a transaction and like its state transition from like the previous state root to the next state root comes out to maybe for an average block around like 1 to 2 cents, which is already super good because like for normal transactions, the Ethereum data availability costs are like at least 10 to 20 cents. And so yeah, the proving overhead today already is like pretty cheap for transactions, and yeah, only going down.
Can we, though, just to be complete here, once you generate the proof, you also have to validate or verify the proof on, at least on a block. If we're using it in a blockchain context, we have to verify the proof. What is, and I mean, this very much depends on what chain you're on, but like, what does it roughly cost in dollars or maybe gas units to verify these proofs on different chains?
Yeah, so I mean, the gas costs are pretty negligible on all chains except for Ethereum. But on Ethereum mainnet, it's like 250K gas, which, yeah, I mean, it depends on the ETH price and things and the gas price and things like that.
But it's like, that's like now it's like more than 100, 200 bucks, I think. Something like that.
That sounds, or yeah, I don't know. I think gas might have been a lot recently. That sounds kind of high, but I think back when I was looking at it, it was maybe like $20. Yeah, maybe recently it's gone up because ETH went up, obviously, and then the gas price has also gone up.
Yeah. And in terms of on a layer 2, is there like a lot of call data or other costs associated with validating one of these proofs?
The call data is actually pretty negligible on a layer 2. Like that probably costs like, back when we were verifying proofs, it was maybe like 20 to 50 cents is my best guess. Don't quote me on those numbers, but I think it was like in that range where you just pay for call data. Obviously, computation on a layer 2 is like basically free. So yeah, it wasn't too bad. But I think there's this kind of myth, I think, for ZK that like, oh, it's so expensive, it's gonna cost so much money. And I think historically that has been true, but just like every year things are getting orders of magnitude better and like the cost curves are coming down so much. And so I think even today with the numbers we have, like it's 1 cent or 2 cents a transaction. Like that's already awesome. Like that's already something that's very feasible right now. For Tendermint, also it's like a couple pennies per Tendermint proof. So I think there's this kind of big myth about ZK that it's like too expensive, and I think that's just like not even true right now. And I think there needs to be like education done on that.
And Uma, isn't aggregation a part of this story as well? Like, can't you aggregate some of these proofs together and then that ends up making it cheaper?
Oh yeah, 100%. Yeah, so as Hart mentioned, like if you want to verify a proof on Ethereum today, it's like pretty expensive. But what's awesome about ZK is you can verify a ZK proof in a ZK proof. So we call that recursion. And basically all ZK systems use that, like rollups use that a lot. Even we use that for our bridges and stuff like that. And with recursion, you can just like compress an arbitrary amount of computation into one proof. And so for what a lot of like layer 2 rollups do is like they'll have maybe one proof per block, then they aggregate all those proofs across a chain of blocks. So maybe like every 3 hours, they'll aggregate all the proofs they've generated across those 3 hours into one proof, and then they'll verify that proof on chain. So you only pay that amortized like 250K gas every 3 hours or something. And in general, like you can actually aggregate arbitrarily many computations into one. And so I think in the end, the amortized cost for aggregating a proof on Ethereum should basically go to zero because everyone will be aggregating all their proofs together.
Yep, that makes sense. And I just double checked. So 250K gas is like $70 right now.
Oh, right now. Oh, wow. What is the gas? What is the GOI right now?
It's like 80 Gwei, but
Oh,
like
okay.
ETH price has gone up, like, but like this all $70 amortized over many transactions is completely reasonable, right?
Yeah, totally.
And like, this is the way a cross works too, right? Like we batch together all of our intent verification and amortize it over hundreds or thousands of transactions and makes it cheap. So I'm a big believer in that concept. I did kind of think it would be worthwhile, though, going into some of the limitations of ZK here from an interop perspective, too. Because I think there, I have come to believe that this is like incredibly powerful and transformational technology. But I also think at times people think they don't always push on the limitations of what it allows us. So I was thinking through some examples that I was hoping I could walk you through, and you could tell me where I'm wrong or help me make sense of things. So, proof of work blockchain. Proof of work blockchain is basically one giant computation. And so at any point in time, I could do a ZK proof of that whole computation up to the current state root of that blockchain, right? But the problem would be I could also then mine one additional block that I mine, that I control and do bad things in. And as long as I can generate one additional block, I could make a ZK proof on that one additional block, right? And then my ZK proof would be valid, but it would be for a bad state root. Yeah?
Yeah, so for example, if you wanted to make a Bitcoin to Ethereum like client using ZK, you have to be kind of careful because, as Hart is saying, like, I can just mine like my own fork of the chain that's malicious, and then what happens is when I verify that on Ethereum, like, sure, it is the longest chain by amount of work, but it's like not really the valid chain because no one else is like updating that like client. So if you have just a like longest chain based like client on Ethereum for something like Bitcoin, there's like a strong liveness assumption that like that like client is getting pinged often by many different people with like the latest blocks and the latest amount of work, so that you can't just have this like malicious fork.
Or you could do something where you like prove the ZK root for the current state root, but then look back 10 blocks or 15 blocks and be like, okay, here's where I actually want to say, here's the data I'm trying to say is true. Because the cost to generate 10 or 15 blocks right now would be so astronomically high, you could put like an economic guarantee around that or do things like that, right?
Yeah. You can, yeah. So I think in general for most Bitcoin like clients, they do that where it's like you do longest chain and then you walk back a bunch. So you could definitely do that. Another great thing you could do is you could prove like basically you prove like the state transition validity with the ZK proof. So not only do you just prove like, hey, here's like a header with the most work attached to it, you also prove that like, oh, all the headers are connected with a valid state transition of like the UTXOs with valid signatures and stuff like that. And then that makes your guarantees like significantly better. Obviously, it still might not be the canonical chain, but at least then you can't just be like, "Oh, my balance on Bitcoin is like 1 million," because like there would never be a valid transaction that would make your balance like an arbitrary number. So you can still do the double spend attack, but you can't just like set your balance to something arbitrary.
Okay. Yeah. So basically, what you're saying is like, if we're proving computation, which we're doing with proof of work blockchains, because you can theoretically compute the blockchain, you got to do some work to put like guarantees around how difficult it would be to do that computation ish, right? Okay. Now, proof of stake blockchains like Ethereum, as I understand it, right, you can do this ZK proof on the current state of Ethereum or on the state transition of Ethereum, but Ethereum finality comes from this like sync committee concept. Actually, I don't want to keep talking. Why don't you talk about like what are the limitations around how I can transport the current state of Ethereum in a ZK proof to other chains?
Yeah, so Ethereum's like consensus mechanism finalizes after like 2 epochs, which are like 6 minutes each. So that's why Ethereum has this like 12-minute finality delay. So even with zero knowledge proofs, you're never gonna like increase Ethereum's finality. So there's always gonna be room for things like a cross where like if I want my money on the other side from Ethereum faster than 12 minutes, I'm going to need someone like a Cross to basically eat the finality risk and then provide me money on the other side. And like that actually seems like a great use case for something like a Cross that ZK doesn't solve, because like there's no computation you could prove that Ethereum has finalized before 12 minutes because it just hasn't. So that's like one limitation of zero knowledge proofs. I think the other thing is Ethereum right now has Ethereum's consensus protocol has basically like around 1 million or something BLS signatures. BLS public keys that kind of like get aggregated into one BLS signature to prove across like the finality of the chain. This is because they have this like 32 ETH staking thing where you can only deposit 32 ETH, and each 32 ETH is associated with a public key. In practice, there's actually only maybe 10,000 or 13,000 like logically different validator entities, and like they're working on this like max validator balance that will increase the 32 ETH a lot. So it reduces load on the network. But right now, if you want to like prove that 2/3 of the entire Ethereum validator set have signed off on a particular block, which is needed for finality, it's like a really, really, really large computation, because like you're having to basically prove that these 2/3 of 1 million public keys have like signed off on something. So that's very hard to do in a zero knowledge proof, because like zero knowledge proofs already have a lot of overhead, and then on top of that, you're proving this like really, really expensive computation. So Ethereum came up with this protocol called the Sync Committee, where basically they choose 512 random validators. That's like a subset of their million validator public key list. And then those 512 validators sign off on the headers. And basically you can like verify the Sync Committee's signature instead of having to verify from the entire validator set. Now, the Sync Committee, statistically speaking, because it's randomly chosen, is very likely to have like the same portion of honest validators as Ethereum itself. So like the probability the Sync Committee is honest is like very, very high, because like we're already making the assumption that 2/3 of the Ethereum validators are honest. But obviously it doesn't have the exact same guarantees as Ethereum, because it's like this probabilistic sampling thing, if that makes sense. So right now in a zero knowledge proof for us, for our Ethereum proofs of consensus, we always verify the Sync Committee, not like full Ethereum consensus, because the overhead of that computation is just very high. So that's like kind of another limitation, is like the Sync Committee's properties are just like not the same as like full Ethereum consensus. And so yeah, some people think that that's kind of bad.
So but basically you're saying that the efficient way to do a ZK proof on the state of Ethereum today is to make a proof that these 512 Sync community validators signed off and finalized a block. And then you can, and that's after the 12-minute epoch has passed. And then I can make a ZK proof around that. That ZK proof costs me a couple cents to make, and I can export it anywhere. Yes. Okay. And there might be other things that I think we've gone deep enough, and this is actually super fascinating, but like how the Sync community gets picked and how you know who the Sync committee is, but like, let's leave that aside for now. So there are some limitations there around this. And then just for the audience too, if I want to make a ZK proof on an optimistic rollup, so on Arbitrum or Optimism, technically, because they don't have finality for 7 days, if I'm going to be like purist about it, I can't really make that ZK proof of the state of Optimism or Arbitrum for that 7-day period. Is that right? Is that like kind of inaccurate, or how would you like think through that?
I mean, you can make a zero knowledge proof of Optimism and Arbitrum state transition function. I mean, my real, maybe spicy take is just like Optimism and Arbitrum are going to become ZK rollups before everyone thinks they will be. Like, I just think the tech is ready. It's pretty cheap. And like, why wouldn't you have the best tech, you know? Like, why wouldn't you have like the future of tech securing your rollup? So I think they will become zero knowledge proofs in a much shorter amount of time than people think, but I'm obviously very biased. So today you could make a zero knowledge proof of Optimism or Arbitrum state transition function. Now, like, but so that is something you could do if you like coded their state transition function and like took their call data from Ethereum and were like, hey, when you have all this call data and you do this stuff, it results in this new state transition. But in an optimistic, if you don't do that fully in an optimistic system, yeah, you can't have finality for like 7 days just because like you need that like challenge period basically.
And yeah, and then there's like Lagrange is one team that's working on like a thing to get more finality from optimistic rollups and stuff like that too. Right?
Yeah, they're working on this like basically economic security solution where like you have the eigenlayer or node operators who are economically bonded, like sign off with economic security on optimism and arbitrum state roots, and then they get slashed later. So that's like one intermediate option. But I think the end game of all of that is just like zero knowledge stuff. Like then you don't even have to worry about operators. You don't have to worry about any of that stuff. You just have like a proof. Like a proof is simple.
Okay. Yeah. Proof. But basically, so to wrap this up, right? If you have a chain with finality, unless you're doing some other mechanism, that you really your cleanest way is you make the ZK proof after you've achieved finality, right? So and you can so ZK proof after 12 minutes for Ethereum, or after like some optimistic time, 7 days for the optimistic rollups. That's like the cleanest way to make these proofs. And if you have a proof of work blockchain, your ZK rollup probably needs to be walked back from the head of the chain to have some economic guarantees around it being not manipulated. Is that you kind of agree with that?
Yeah, so I think it's important to talk about like for different chains, like what is finality. So for example, in Bitcoin, there's never any true finality. It's all probabilistic finality. So yeah, for Bitcoin, like you just have to prove like, hey, here's like the longest chain. And like if I'm walking back a certain amount, it just gives you more and more like economic finality. For Ethereum, you do have like finality with economic security. You just know like, oh, these many people get slashed if this block gets reverted. For a ZK rollup on Ethereum, you have first for a ZK rollup on Ethereum to be finalized, first Ethereum has to finalize. And then on top of that, you have to prove like a ZK proof of the rollup state transition function on top of Ethereum. So like on top of all the call data posted to Ethereum. And then for an optimistic rollup's or for any rollup on Ethereum, it's actually finalized once all the data is on Ethereum and finalized. But the state root might not be available on Ethereum for a while because of either this like optimistic challenge process or like the ZK proof verification doesn't happen every 12 minutes. It like happens every 3 hours just because like posting a proof to Ethereum is expensive. But the rollup itself is still finalized, if that makes sense.
Yep.
So
I love this. Okay, keep
yeah.
going. Sorry.
Or sorry, this is like really deep into like
Well,
blockchain architecture.
But the point here I want to make, and this is where I think we're gonna like lose the listeners, and I don't want to go any further, right? But the utility of like ZK tech is related at a pretty fundamental level to blockchain architectures, I think, from like an interop perspective. And although it's like it is clearly the future, in my opinion, and clearly the way these networks should be connected, there is some latency concerns. So we basically get maximum security, but we probably have some latency concerns because many of these chains don't achieve finality particularly quickly, right?
I think basically at the highest level, zero knowledge tech can make you achieve finality faster because if Ethereum, like rollups actually do have finality fairly quickly. It's like as soon as Ethereum's finalized and all the DA is available, they are finalized. It's just like you can't bridge out of them and you can't interoperate them because like it's hard to prove that finality to someone else. But then with a zero knowledge proof, you can prove that finality very quickly because like the computation is already true after like the 12 minutes. So that like zero knowledge proofs are useful for just like finalizing things faster and like having a validity proof of that like as fast as possible.
Hey everyone, this episode is brought to you by Uniswap, delivering the best on-chain trading experience, period, bar none, in all of crypto. Here's how I would divide the protocol today. There's a web part, a mobile part, and an extension part. You can say goodbye to the pop-up wallet extension. It's just not great from a UX perspective. Now what they've delivered is this nice, clean sidebar where you can just very easily track swaps, sign transactions, send or receive crypto anywhere. Just a huge UX improvement. On the web part of it, huge improvements here. You can buy and sell 700 plus tokens at your price on your terms, and they've got limit orders, which are powered by Uniswap X, and there's gasless. They've also got real-time charts, transaction logs, pool data, project information, all this cool stuff that just really improves your UX trading on the web. And again, all of this is powered by the smartest protocol in terms of Uniswap or Uniswap X. Click the link at the bottom. Uniswap extension is in alpha right now, and we'll see what you can do about getting you moved up that list. Thank you very much, Uniswap. I want to get a sense of like how you see ZK playing a role within Interop. And we've been talking to so far this season. Actually, Chris Goes of Anoma sort of painted this world, right, where you kind of have within the Anoma framework, there are these heterogeneous environments, sort of call them computing environments. And one of the big light bulb moments for him that he introduced to us very early on in the season is that the thing that changed and makes Interop work within the Anoma framework and sort of blockchains more generally is ZK proofs. And I guess probably just because it's been in the zeitgeist a little bit, like this kind of the Polygon sort of ag layer type thing as well, right? Where you've got their CDK, their chain developer kit, where you can spin up multiple different chains, and the way that they're going to talk to one another is there's kind of a two chains that want to talk. Proofs are generated, they're aggregated at this layer, then posted down to Ethereum, and that all sounds very good. I think there might be some limitations to that, and Hart was getting at it a little bit with the latency discussion. But I mean, Uma, when you broadly kind of think about ZK proofs, how do you think about that within the context of Interop? What does that bring out or enable?
So yeah, I think for Interop today, for example, first of all, I think let's talk about like optimistic rollups. I think it's very hard to scale Interop with optimistic rollups, even for people like Across, where the rollups actually reach finality very quickly because they'll post all their data, and once the data is on Ethereum, it works. But then these relayers, in order to get paid back, like the withdrawal window from these rollups to transfer assets is like 7 days. And so Hart's relayers on Across, or whoever's doing the relaying on Across, has to wait 7 days for their capital to be like withdrawn. And that's just like very inefficient. And so I think with zero knowledge proofs, you can just have much quicker finality because you don't have to wait for this like challenge period, 7-day thing. You can just have a proof posted within like a couple hours. And so it just like really improves capital efficiency for Interop. And I think that's like really exciting because it's just unlocking like so much more capital.
I'll add one other thing. One other thing there too, Uma, like if there ever is like a fault proof or whatever, like fault proofs in the optimistic system are just very messy to deal with, and like the ZK stuff just is like way cleaner because, like you said, it's a proof. So I'll further add that like dealing with fault proofs on optimistic systems just seems like a whole messy can of worms that nobody really wants to deal with. But keep going. I interrupted you.
Yeah. They're planned for like, oh, if there's ever a fraud, it's like, oh well, or that it's just something much cleaner to just have like, I always say like ZK is like truth, and it's just like it's very much cleaner because you're just like, I prove this function happened. So yeah, I think capital efficiency is really nice. I also think, for example, for Across today, all these like we're like rapidly in this world where there's like thousands and thousands of rollups, right? Like you can go to Conduit or like Caldera or whatever, and like I could like even spin up a rollup in like 2 minutes. And so for all these different rollups, it's really hard for someone like Across to like support all of them because like you have to run all their nodes, and like that actually costs a lot in AWS. And yeah, you have to like run all this infrastructure. And so that like fundamentally doesn't scale super well. And with a zero knowledge proof, it's like maybe one day Across doesn't even have to like run a node for a different chain. It can just like verify a proof that like this happened and then be like, okay, like let's do the relaying or stuff like that. And so I think that's also like pretty powerful. So I think those are like the exciting applications of ZK and Interop. Also, even moving out of rollups, we're still in a world where there's like a ton of L1s. And for L1 to L1 bridging, you basically today the status quo is like you have some multi-sig of like 5 people, and then you have like someone deposits money on one side, the multi-sig says, yep, okay, the money was deposited, and then they unlock tokens on the other side, or they mint tokens on the other side. And that's obviously very risky because these multi-sigs can get hacked because like, you just have like 5 people, you just hack into an AWS account or 2, and suddenly like the keys get compromised. And if instead on the other side you're verifying a zero knowledge proof that like the original validators of the source chain actually signed off on a current state of the world, it's just much more secure because that's like very hard to forge. So I think, yeah, cross-sell, like replacing multi-sigs and making cross-sell one bridging way more secure is very exciting. And then transitioning all rollups to 0 ZK rollups and unlocking like capital efficiency and like more seamless, smooth interop and like better scalability across thousands of rollups is also really exciting.
Okay, Uma, I'd love to get your opinion on the overall demand for like how useful synchronous versus async composability ultimately is, because that's one of the limitations here, at least my understanding of like roll up to roll up interop that gets facilitated by ZK. That's async, right? That's not happening at the exact same time. And like maybe to challenge a little bit how useful that is one of the reasons why people are extremely excited about, or at least at one point we're really excited about that interoperability. There's a MEV aspect to this, right? Where you could do some sort of like at the simplest form, like an arbitrage between two different dexes. And in this world, you could maybe place a trade where there are multiple legs. You submit a proof which corresponds to each leg that gets aggregated into this one layer and then posted. And then that's very simple. The problem, as we've talked about a little bit, is like the latency there, because again, like Ethereum moves in 12-second block times, and 5 minutes there kind of limits that specific use case. So I guess, what are your thoughts on the limitations that the latency in this world has on different, sort of cross-chain use cases?
Yeah, so cross-chain MEV is like an interesting topic because I feel like a lot of people are excited about it, but I think so. Okay, at the highest level, you could argue like the real cross-chain MEV is like the rollups and like Binance or like centralized exchanges, because like those people are always gonna have a faster block time than anything decentralized. So one could argue, well, is there even gonna be like cross rollup A, cross rollup B arb when like the true leg is really rollup A to Binance, rollup B to Binance, and then like, or I mean maybe that's not super ideal, but like that does feel like that's gonna probably be like the most important volume, at least for a long time. So there's a question of like, does cross-chain MEV even really matter? Even if it's async, the second thing is, I guess if you have synchronous interop across two different chains, fundamentally, I think the proposer, like the person who is deciding what that block is, has to be the same entity. The chains can be separate, but like the proposer at that point has to be the same entity. And so that can happen with ZK, without ZK, whatever, if that makes sense. There I think the proposer / sequencer is like the most important person, not the validity mechanism, if that makes sense.
It does make sense. And I think it's a nuanced and interesting and tricky point. But I think where I'm aligning, and Mike, we still have more episodes in this season to try to hash this out. But if you want synchronous cross-chain things, the block proposer is got to be proposing that same block on both those chains. And in a sense, it almost looks like they're the same chain, but not. And maybe there's sort of like some weird nuance here where they're separate chains most of the time, but every so often when they need the synchronous thing, there's like a block that is proposed by the same entity and it kind of becomes the same chain for that moment. Anyways, I think that does make sense, Uma, but it's definitely a nuanced point.
Yeah.
And yeah, regardless, what you're saying here is to just reiterate the stuff that's really like in my brain. And it's like ZK becomes this glue to connect disparate systems with quote unquote truths, because you literally just have a math proof of what the truth is. Your limiting factor here is that in order to create that proof of truth, you need that chain to achieve its true truth, like which is aka finality, right? Which kind of makes total sense. If it's at some intermediate state where it's not fully proven on that chain, then you can't quite do the proof of truth. Yeah, I don't know. That just seems really powerful.
Yeah, I agree.
So Uma, if this is already really cheap, the latency doesn't ultimately end up mattering that much. Why aren't we aggregating all of why doesn't it feel like all these chains are basically one? Why isn't everyone doing this today?
I asked myself that question too, Mike. I
Just
think
not
the truth
visionaries
is,
like you, Uma. That's the problem.
no. I think, okay, a couple of things. So I think historically, to use ZK, you'd have to have this team with like really built out ZK expertise. Like, you'd have to be a ZK wizard. You'd have to have a whole cryptography team. You'd have to build your own proof system. You'd hand roll your proof system. It sucked. We did that for all our bridges, and it's just not very sustainable. I think there's been this recent wave of ZK VMs where basically it allows any team to just like express their computation in like Rust or like normal code and then get that proven for a cheap enough cost. And that's what like things like SP1 kind of enable, is like you can get like all the performance you ever wanted, but you can still write it in normal code. And that combination of like amazing developer experience plus amazing performance, like that combination is, I think, what's been kind of missing until this point. And now with things like SP1, I feel like it's kind of at like the turning point where it's like the DevX is good enough and the cost is cheap enough where now everyone can go adopt it. So like, and that only came out like a few weeks ago. So I'm very optimistic that like hopefully this is kind of like the turning point for ZK, where like suddenly even teams that have pursued an optimistic approach for a long time are like, oh wow, like now the tech is good enough and like now the tech is cheap enough. Like, let's go do it, you know?
Yeah, like Uma, I guess just to push on this is so recent, right? Like SP1, you guys announced, but is it mainnet or what do you call it, DevNet right now too?
Right now it's right now it's just like still like alpha mode, like it's not intended for production use. That's like our highest priority as a team and like what we're working on very actively towards. So hopefully that comes soon. Like we hope in like a few months. So yeah, that is also a bottleneck.
Yeah, well, okay, but like it's just we're like of the moment. Like you guys have just put this out. Risk Zero, sort of in the same space, is coming out soon, like very soon too. I think there's another project, Gevulot, that's like Prover Network. All this stuff is like not like this is the point why I think the next 6 months to a year are going to be super impactful, because these tools are really truly going to be live and usable with a good developer experience.
Yes, exactly. No, yeah, to answer your question, Mike, I mean, I was kind of joking before, like, I think a lot of this, like, stuff is really new. So, historically, ZK has been very hard to use, and its performance is bad. Then a lot of people fix the performance, but it's still really hard to use. And then now with things like SP1, it's like you get the best of both worlds. But SP1 obviously is very recent. I think it's like a month old at this point. So now it's kind of like, okay, now people can start like thinking seriously about it. And so
But this is
that's why
exactly why we want to talk to you. It's the frontier. You are the frontier,
Yeah.
Uma. So, right.
Uma,
that's too nice.
Can you help us think through what are some of the second order implications of if ZK tech were widely adopted? How would that change blockchain architecture and sort of where value accrues? Like, here's one thing I was thinking about. So, one of the layers that network effects accrue to is at the execution layer. We see massive returns to the EVM. Now we're seeing it with the SVM, and maybe this like move ecosystem ends up being valuable as well. But one of the, at least when I think through how computing changes with ZK, is like suddenly it doesn't really matter what execution environment you're using. And like most of that computation happens off chain. And then these sort of proofs, there's like some new kind of aggregation layer that ultimately ends up happening. And then a lot of blockchains, as we think about them, are just kind of like bulletin boards, right? And that's like where I understand the sort of Celestia vision going, the Ethereum vision going. So, I mean, does that make execution environments slightly less valuable? Like, what are, just help us think through like some of these second order implications if this were to be widely adopted.
Yeah, it's interesting. I feel like if ZK proofs become widely adopted, there's kind of like, it adds like a new layer to the modular stack. So like there's data availability and consensus, which is like, one part of the modular stack. There's settlement, which is kind of like what asset you're using, where's all the bridging happening. So like, for example, right now, like I think a lot of people use Ethereum as a settlement layer. So that's another part of the modular stack. There will be like proving, which becomes a part of the modular stack, which is like, how are you actually getting your validity proofs to like settle to the settlement layer? And then there's actually like the user facing stuff, which is like, what network are they using and things like that. In terms of value accrual, I mean, I obviously think like proving will be very important, and it'll be more of like a volume thing where it's like, oh, you just pay like 1 cent or maybe even a fraction of a cent for a proof. But like there's so many, every user interaction with the chain will use a proof. And so that will be like, proving will be like a volume based thing where it maybe ends up making a lot of money, but like it's just because there's so many proofs being generated. I think obviously the economics of like settlement look pretty different because like it's like, oh, ETH is money, and so there's like monetary premium, and then like maybe with DA there's like I don't know like what the value accrual story looks like there, but that's just like another part of the stack. So yeah, I guess it's hard for me to say, but I think the TLDR for me is like there will be another really important piece of the modular stack in addition to execution, or in addition to DA and settlement and execution. There's also like now there will be like proving.
Mm.
So that is another question I have in my mind for you, Uma, too, where it's like, how many of these proofs do you think there are in this? And like, and I think there's going to be this evolution here too. So if a proof takes 5 minutes to generate right now, it's not in my mind, it doesn't make sense for there to be like 10 million proofs being generated a day from like at least an interop perspective, because you're going to batch your messages and send them every 10 minutes or something like that. But I still think the ZK component here is incredibly valuable because you are sending truth like every 10 minutes. And sidebar, this fits into like our across thesis very well because across like batches together repayments every hour or whatever. But this sort of runs counter to, I think, the thesis of a lot of other messaging frameworks. Axelar, Wormhole, Layer Zero, I think they're all kind of built around this idea that there's going to be tens of millions of messages getting sent between blockchains. And I'm kind of curious, but that are not necessarily ZK, right? And I'm kind of curious where your mind goes, where if ZK takes 5 minutes to generate now and it's going to take 30 seconds later, but we're not down to 200 millisecond proof times or 20 millisecond proof times for a while, I think. How many ZK messages do you think, or ZK proofs, are getting generated in a year from now? And like, how does that influence blockchain interop and like architecture?
I think, for example, for a ZK rollup, it's kind of like there's not a proof generated for individual transaction, but there's like a proof generated for the entire block. And maybe actually there's like proofs generated for every block that get aggregated together. So in the end, it's kind of like every transaction does trigger a proof. It just might not, like, it might just be everything's like batched together. And so I think with messaging, it could be pretty similar where it's like maybe not literally every single individual message triggers a proof, but you have a proof that like, oh, Ethereum came to finality on this batch of blocks, and then, oh, I have like 15 messages that were contained in that range. I think obviously there will always be like non-ZK solutions for things that where it's like maybe the finality doesn't matter as much, or like the security doesn't matter as much. And so yeah, I don't necessarily see like, oh, everything has to be ZK all at once. I just think like more and more things will like transition towards that, starting with like the highest value use cases. So like for example, right now I feel like rollups being ZK rollups makes a ton of sense because like they have a ton of TVL on the line, and like I'm sure if you're a rollup team, it's really stressful to operate one, and like adding ZK security adds like your peace of mind, if that makes sense. And then I think as it gets cheaper and cheaper, like more and more people will like just start using it because it's like, why not? So that's kind of how I see it evolving.
Okay, so this is actually kind of interesting. So if you're doing a ZK proof of each block, and then every I don't know, 100 blocks, you're doing a ZK proof of those 100 blocks recursively, and then posting that to Ethereum, let's say, right? And if your block time is 2 seconds, I just did some math. That means you're making 43,000 plus a little bit overhead, making like 45,000 ZK proofs a day. And then in a world of 1,000 rollups, you're making millions of ZK proofs a day here. Okay, cool. So this is like good business then for people doing ZK things, where if we have a world of 1,000 rollups or 10,000 rollups, all ZK based, they're doing a shit ton of ZK proofs. On the interop side, maybe that's true, maybe that's not true though, because if you aren't able to make those ZK proofs immediately anyways because of finality concerns, like you have to wait for chain finality, then probably does make sense to batch them together. And so maybe you like you said, you don't have nearly as many ZK proofs between blockchains, but they're just really useful. I don't know.
Yeah, I can imagine that happening. Yeah.
Interesting. Okay. I'm learning things.
I should ask Uma. This is probably a really basic question to ask right at the end of the podcast, but like in L1 to L1, like communication that makes use of like a ZK like line or something like that, do you still need a general message passing protocol like or transport layer like layer 0 to deliver that, or no?
Yeah, like layer 0 actually is like this, and I think a lot of other protocols like Hyperlane and stuff are like modular. So basically, like they just provide you smart contracts and kind of like this framework for sending messages. But then the security mechanism of how the messages are delivered can be abstracted away. So like you can use layer 0's multisig, you can use ZK proofs, you can use Succinct ZK proofs, you can use someone else's ZK proofs, you can use like some other system. So you still need the messaging framework because like you still need like the solidity side of things to like keep track of the messages. You still need like the relayers, like all that kind of stuff. And then the security mechanisms like abstracted out and can be either ZK or not ZK. So yeah, I think yes, you still need layer 0. Like we would, for example, work with a team like layer 0. Like we work with Wormhole to like help provide them their ZK security. And so we could also work with a team like layer 0 to help add a ZK Oracle to like their protocol.
Awesome. Uma, in conclusion, like one sort of big question we've been asking guests from this season is, as crypto grows and there are many different chains and many rollups that exist, obviously the space is getting more complicated. Sometimes these solutions, like the best solutions, end up taking a really long time to get to market. Other solutions that maybe accept some less positive trade-offs or cut corners kind of end up happening, and we kind of have to have these very hard conversations with ourselves about trade-offs. And something Hart and I've been questioning is like, what ultimately would be a good end state for crypto and this sort of on like a 10 to 15 year time horizon? Like if we accomplish something here as this industry in this future, like what would be a successful outcome from your perspective?
Like with regards to ZK or like more broadly?
More broadly, but like theoretically, maybe you spend a lot of time with ZK, so I'm assuming that's part of the vision.
Yeah, I think at the ZK level, like I just think ZK is like simple because it's just such a fundamentally simple, like it's not simple to implement. Like our team knows that. But like once you have it, it's just such a simple primitive. It's like I have some function, I proved to you the function is like this value with this input. Okay, now you're good to go. And it's just like I like to tell people it's like ZK is like truth and like the truth is simple. And so I just see ZK being integrated into everywhere. Like I think every bridge will be a ZK bridge. I think every rollup will be a ZK rollup. I think basically all blockchain infrastructure will like run on ZK rails and it'll all be like seamlessly interoperable. It'll be like all verifiable. There's none of this like complicated optimistic stuff. There's none of this complicated multi-sig stuff. It's just like verifiable compute being used everywhere. That's kind of like the end game vision I see for all this like blockchain infrastructure stuff is like ZK is like the glue that holds everything together. And that's actually why it's like a great fit for an interop episode because interop's all about glue. And I think ZK is kind of like the ultimate glue. That's not to say there won't be more layers. Like, for example, I think there will always still be room for a cross because like, sometimes you do need to eat finality risk. Yeah, woo heart. I do think there's obviously going to be room for wallets. There will always be room for wallets who like provide a really seamless user experience and like integrate with across or like stuff like that. There's always going to be room for aggregators. Like there's still going to be many layers of a stack, but I just think ZK is going to be like the base glue for everything and like basically yes, like having truth communicated everywhere. Yeah, so that's kind of the end game of how I see the space evolving and how I see things talking to each other. And hopefully that leads to like better security, like no more hacks and like leads to like, oh, there's not rollups that are just multi-sigs with like no fraud proofs and stuff. It's just like everything hopefully will just
which
use
rollup
ZK.
Which rollup are you talking about?
Hey.
We don't name names.
I think Mike is going to wrap this episode, but actually, yeah. Uma, I want to ask you one other question. What's your most exciting use case for ZK outside of blockchains? I think I have a guess what you're going to say, but I'm really curious, like where this goes.
I actually have an answer for this too.
Oh,
no. Okay, so Mike and I have our bet. Let's see what you say.
I think some of the attested image editing stuff is really exciting and interesting. Like basically you have some attested sensor, but none of the images you see on like Facebook and stuff are like the raw sensor data because that's like way too big. And basically you can just prove like this image was taken from like a camera and then modified with these transformations and like JPEG compressed and cropped and whatever. And then this is like a real image, not from Midjourney. Like, I think that's already super exciting. Actually, some people at a Stanford hackathon tried out attested image editing with SP1, and it was really exciting and interesting. So I'm very excited for that kind of stuff, especially as we get like more and more crazy, like image generation, video generation, whatever.
That was pretty much what I was going to say, something in AI space, which is like, it's like this idea of verifiable compute. So even verifying that an AI ran a computation is interesting too. But the attested imaging stuff, having all our iPhones with like a chip in them that is going to attest that our photos are real, is pretty cool. Mike, what was your guess?
I had such a lame one. I mean, mine is much too optimistic. I don't think it's ever going to happen. But I was listening to this podcast, shout out Dimitri Kofinas, about basically like how the modern surveillance state got created. And we don't need to go like all the way into it, but basically to like drastically dumb down what ended up happening was the US government just created essentially a list of everyone. They're like, in order to make sure that people aren't doing bad things, we just need a whole big list of people. And I don't know how this would actually translate into something like ZK Tech, but I just remember thinking like it would be really nice if we could actually get the desirable government outcome that the government wants, which is like, hey, are you doing like horrible like kiddie porn things online, without just like aggregating all of that in one place? Because that's always been my big problem with the crypto anarchists. Like, governments actually do a lot of shit, like stuff that we really want them to do, and they do have hard jobs. So if we could give them this primitive, this tech building block, maybe actually that could lead to the outcomes that we all want with the privacy that's extremely important.
I like Mike. You're kind of like this like upstanding American, like good taxpayer cypherpunk. It's like a great combination. I kind of love it. So
I'm definitely not like a burn it all down kind of person. Like, I'm actually pretty stoked. I like living in America for the most part. I'd love to not burn it down. But I don't love what's going on now. So I appreciate that, Hart. That's very nice. Uma, if people want to find out more about you, Succinct, what's the best way to do that?
Yeah, you can follow us on Twitter, like at Succinct Labs. And yeah, like we post a bunch of stuff of what we're up to there. Yeah, that's probably the best way.
Okay, cool. This was really fun, Uma. Thanks for joining us.
Thanks, Uma.
Yeah, this was super fun. All right, good to see you guys. All right, bye.
All right, Hart. That was a great episode. Almost made a ton of sense. Like we should just obviously be leaning pretty hard into ZK proofs. What do you think?
Yeah, makes a ton of sense. I mean, I think Uma's brilliant. Full disclosure, I've gotten to know her from like basically day one of her starting Succinct, her company, and she's just like clear thinker, great energy. It's hard to think that same person is like a super nerdy math geek that can do like the crazy moon math in her sleep. And her co-founder John's pretty brilliant too. So just amazing people. And I think like those are the types of folks, and there's a lot of them in the ZK space that are really taking this tech and making it a thing. 3 years ago, the idea of this existing was an impossibility. People just thought that was no way. And this industry is wild. So yeah, the ZK stuff seems like it's a really important part of the stack. And what I really enjoyed about Uma's conversation is like she was also very real about the limitations of it, like where it works and where it doesn't. And I thought that was super, super compelling.
And one thing that we didn't really get into, but Uma originally Succinct was really focused on the bridging sort of application, and then I don't know if pivoted is the right word, but sort of expanded into this new release, this VM, the ZK VM that they just launched, SP1, I believe is the name. And you can hear her on other podcasts sort of talk about going through the pain of developing a ZK application. It was kind of beyond the scope of this podcast, but like how difficult it was to just like debug circuits and stuff like that. And that was actually part of the reason why she decided to build out this more general purpose infrastructure. So I think that was one of the bigger takeaways for me, is that it actually just used to be extremely hard to build these applications out. But now with, Succinct, and I understand RISC-0 does something pretty similar, like I think it's just going to get a lot easier, and there might be this massive Cambrian explosion. And
yeah, absolutely. I mean, it's funny, I can speak because like across, we were working with Succinct on their old product, their bridge product, to actually bridge messages from Ethereum to other L1s like BSC. And it is pretty interesting because I basically think Uma's story here is they were hand rolling and hand tuning all of these circuits for specific use cases. And it was almost like they were becoming like consultants or like service providers that would just build this like circuit for a specific use case. And they're like, this sucks. This isn't scalable. This takes forever. And then they figured out how to abstract it away, which is amazing and makes so much sense. And yeah, they're not the only ones in the space doing it. So we should give a lot of props to all the other great teams in the ZK space that are building cool stuff. But they're an example of a team that was painstakingly tuning their own circuits or writing their own circuits, and they're like, let's abstract this away. And I don't know enough to know exactly how well it works, but from what I've been told and from what I can observe, it works really well. And so that's pretty cool. The other stat that shocked me actually was this like 2 cent kind of proof generation cost. And this is in a specific context. This is like a Tendermint consensus proof, but like that was way cheaper than I was expecting. I thought that was pretty cool too.
Yeah, the cost aspect of it is coming down. The latency aspect of it is coming down. You know where my mind ultimately went was I was drifting back to that first episode that we did with Chris and trying to think about these different environments and how they ultimately end up getting connected. And one thing I've been sort of thinking about is like I'm starting to question this whole modular versus monolithic debate and how much it really makes sense. It's kind of just like if you know what I'm saying? I think so. The way that I'm sort of starting to look at it is which computing actions are coupled tightly. And I think once we solve a lot of the frictions that exist in these ecosystems, it's ultimately going to be like where there's an economic incentive to like tightly couple certain interactions. And I sort of feel like where I'm heading now towards this like ultimate sort of end state is that we're going to basically break all of these blockchains apart into this like super modular sort of framework. But then we're going to get the recoupling of these of certain interactions where it makes sense to actually couple them. And then I kind of just think it sounds like ZK is going to connect everything else for, maybe there's not actually an enormous amount of demand to trade Ethereum on Jupiter, right? But for that, we'll have zero knowledge proofs, and that'll be fine. And then it's like a different system will support trading Solana, right, on Jupiter. So that's where I'm kind of landing on this ultimately.
Yeah, Mike, I like all your questions around, I'll call them business models, like value capture, like where is value going to be captured here? And increasingly, to me, it's coming across like a lot of these systems, there isn't really a moat. It is actually like there's a service that's going to be provided in a highly competitive market at what is going to be extremely low cost. And the value capture is just volume. It's like doing a lot of it really cheaply. And I honestly think that this is, first of all, not a bad thing for a consumer. And when you think about blockchains being permissionless, decentralized organisms, it's almost the way it should be too. So like Uma, we didn't push her on this, but when she was talking about like ZK and how you make money here, it's just like going to generate a shit ton of ZK proofs, going to charge not much more than the cost of them, but a little bit. And it's going to be a volume game. Just kind of like AWS is mostly a volume game. There's like some profit margin, but it's not huge. Right?
Yeah. Well, I think, Sam said this so well in the second episode. It's like all these people are asking about business models and value capture, and that's such a luxury for me because I just want it to work. And I think that's one of the, by the way, people ask all the time, like, why are all these podcasts so technical? It's because the smartest people are still figuring out how to make it work. And they're going to figure out the business model and value capture stuff later on. But I do think it's like one thing I wish we had poked a little bit more on is just the, where value is going to end up getting created on in these proving networks. And there is a lot of interesting stuff going on in different layers of aggregations within ZK. And I think, right, correct me if I'm wrong, but I'm pretty sure that the sort of plan from the Polygon perspective in their ag layer is to kind of have these economies of scale, right, in the aggregation layer. Once you get a whole bunch of these things together, you kind of, batch them up and then submit them down to main chain ETH. And ultimately that ends up being pretty sticky, because if you were submitting this outside of that aggregation layer, it's much more expensive. So there are these kind of interesting games that I can see people starting to play, but maybe it's just too early, and we just got to see how that all shakes out.
Yeah, I mean, I think it's pretty clear to me. Well, if I just gut reaction think about like UMA's like Succinct Labs SP1 business model, they're building a marketplace for provers. Provers are going to be hyper competitive. This is going to talk about a lot of the other things we talk about in our space. It's like the HFT space in finance, so hyper competitive. Maybe there's not a ton of provers because they're super specialized. Uma hinted at like maybe some of these provers build their own hardware, like literally to generate these ZK proofs cheaper. Maybe that happens. But you have a really competitive marketplace of provers that are just there to offer this proving service at the lowest cost. And Succinct's business model here is they're the marketplace for it. And that marketplace can't be usurious or can't charge too high rent, because another marketplace will pop up that's cheaper, but they can charge something for being the central point of where like supply and demand meet. And I think that makes sense.
I do too.
Yeah.
We love a good marketplace model. And you know what? We started. Do you think that's a popular model? Do people like? All right. Here's one interesting place that we could have gone as well, that we like sort of jokingly did at the end. But I do think zero knowledge is one of those areas, and I think Vitalik has actually said that zero knowledge as a technology is comparable to blockchain as a technology in terms of what it unlocks. Like that's the scale that we're operating on here, and it does feel like, you know, there's so much that's been said about how much can you bridge what's really happening in a real world context into a blockchain. I mean, ZK proofs are a really interesting part of that story, right? Like we've called this the Oracle problem, right? Like how do we relay this stuff that's happening in the real world? And one of the things that it seems like ZK proofs do really well is they take these extremely, you know, heterogeneous sort of computing environments, and it spits out this output which you can put onto a blockchain. And that actually, like, ZK kind of could be the missing link in between getting some of this TradFi stuff that we've been talking about forever on crypto rails also. So
yeah, I think it's hugely powerful. I agree. But like emphasizing what you said, like this is a technology is as big as blockchains. That's a big statement, and we should probably fact check it before we say Vitalik said that. But I think he did, or he said something like that.
Well, David told me that Vitalik said that last night, so that's my source.
All right, so we'll fact check this at some point, but like before we say, but I'm willing to go so far to think that Vitalik definitely thinks ZK is a big deal, and we all should, because I think it is one of those like transformational techs that there is a lot. And again, what's so interesting even about the conversation with Uma, the whole thing was about the succinctness property of ZK. We really didn't even get into the privacy bit too. And like there's a whole other unlock of what the privacy stuff gives us as well, that I think is, frankly, that's where I've spent less of my own brain power thinking through what the implications of that are. But there's like, it's like one technology that gives you two major unlocks at the same time. And that's pretty wild.
I agree. And I've actually decided I'm going to, for the intro to the show, when I do it, I'm going to walk you through, but getting ready for the show, I actually did on Wikipedia, there are a couple of like very plain world sort of examples of how the ZK and the privacy model work. And the privacy stuff, I mean, again, going back to our conversation with Chris, like that was super important to him. He actually viewed that as a fundamental issue with how blockchains are designed for all these different reasons. It's just very suboptimal to have your transactions revealed, either because, you know, people have a right to privacy and people don't want to be exposed, or because, you know, some bot can come in and grab your transaction and then sandwich you, right? Like there are all these great reasons why privacy should actually be at the core of the design. And yeah, we didn't really get into that, but I agree. Hart, this was a really fun one, my friend. I will see you same time next week. Cheers now.
See you next week, Mike.
Hey everyone, want to give a final shout out to this episode's title sponsor, Sei. Now, there are a whole bunch of really exciting reasons to be building on Sei v2 outside of just parallelization. I want you to head over to sei.io to looking into building on their public devnet. Again, click the link at the bottom of this episode and head over to sei.io to start building something today.